Separation of copper and nickel using the provided ingredients. To separate copper, Cu, and nickel, AE, from a solution or mixture, their differing chemical properties, e.g. reactivity, complexation, and solubility, can be exploited. Based on the ingredients from the pantry, the following procedures can be used. 1. Separation of copper and nickel. Exploiting selective precipitation. Nickel and copper can be separated using their different solubility profiles with specific reagents. 1. Precipitation of copper as copper sulfide. CUS. Use dry sulfur crystals to precipitate copper selectively from the solution. Plus how to right arrow QS sulfur to the solution under mild heat to ensure reaction efficiency. Copper sulfide is insoluble in acidic and neutral conditions, while nickel sulfide remains relatively soluble at low concentrations of sulfide ions. 2. Precipitation of nickel as nickel hydroxide. NiOH2. After removing copper, increase the pH of the solution using sodium hydroxide NaOH or potassium hydroxide KOH to precipitate nickel as nickel hydroxide. Need to first to which of right arrow 9OH2 bar. Nickel hydroxide precipitates at a pH of about 8 to 9, whereas copper will already be removed as sulfide or remain soluble in higher pH conditions. Find 2. Using ammonia complexation, copper and nickel can also be separated based on their differing abilities to form soluble ammonia complexes. Selective dissolution of copper. Uses sodium hydroxide, NaOH, and ammonia to create a basic ammoniacal solution. Copper forms a soluble tetraamine copper 2 complex. Plus 4NH3, right arrow, QNH3. Nickel, in contrast, forms weaker ammonia complexes and may precipitate as nickel hydroxide. 2. Precipitation of nickel. After dissolving copper, the remaining nickel can be precipitated using sodium hydroxide, as described in step 112 bar 13. Sequential acid leaching. Copper and nickel can also be separated using selective leaching with acids. 1. Selective leaching of copper using hydrochloric acid. Add 20% hydrochloric acid HCl to the mixture. Copper dissolves readily to form copper chloride, while nickel remains insoluble under controlled conditions. Cu plus 2HCl, right arrow, CuCl2 plus H2, Dapper 2. Leaching nickel with sulfamic acid. After separating copper, treat the residue with sulfamic acid to dissolve nickel selectively. Me plus 2NH2SO3H. Right arrow, SO3NH2 plus H2. Solubility of silver in nickel complexes. Silver H add will remain completely insoluble in the presence of nickel complexes under most hydrometallurgical conditions. This is because 1. Silver's noble character. Silver is a noble metal with low reactivity and does not form soluble complexes with ammonia, sulfamic acid, or sulfates under normal conditions. It generally precipitates as an insoluble residue in processes involving copper and nickel. 2. Selective precipitation. Silver remains as an insoluble chloride, or metallic silver during acid leaching or complexation reactions. Example: workflow for separation of copper, nickel, and silver. 1. Step 1. Removal of silver by hydrochloric acid HCl to the mixture to dissolve copper and nickel, leaving silver as insoluble high AgCl half. Filter the solution to separate silver chloride. 2. Step 2. Separation of copper. Precipitate copper using sulfur crystals to the remaining solution to precipitate nickel as nickel hydroxide by adding cyanide OH2 per half. Filter and dry the nickel hydroxide. 4. Step 4. Refinement of products. Reduce copper sulfide and nickel hydroxide to their metallic forms using oxalic acid or other reducing agents for purity. Conclusion using the provided reagents. Copper and nickel can be separated effectively through selective precipitation or complexation, while silver remains insoluble and can be filtered out as a residue. This approach ensures high purity recovery of all three metals.
Separation and refinement of copper and silver from a mixed precipitate. A hydrometallurgical approach. Abstract. This essay outlines multiple procedural pathways to separate and refine copper and silver from a muddy mixture of precipitated metals, originating from a reaction involving oxalic acid, isopropyl alcohol, sodium chloride, and electrolysis. Utilizing hydrometallurgical techniques and simple chemical procedures, the aim is to achieve high purity metallic powders of copper and silver for subsequent melting into bullion. The processes prioritize rudimentary methods such as precipitation, decantation, and time-based settling, while leveraging reagents available in the chemical pantry provided. 1. Introduction. The separation of copper, Cu, and silver, Ag, from a mixed precipitate requires leveraging their differing chemical reactivities, solubility profiles, and affinities for specific reactants. Copper, a base metal, is more reactive and prone to oxidation compared to silver, a noble metal. These differences can be exploited to selectively dissolve, precipitate, or extract each metal as a separate compound, which can then be reduced to its metallic state. The following steps outline several pathways for achieving this goal, relying exclusively on hydrometallurgical techniques. Materials and reagents. The following materials are utilized in the procedures. Clean treated tap water as solvent and washing agent. Hydrochloric acid, AHCl, 20% liquid. Sodium hydroxide, NaOH, dry crystals. Oxalic acid, dry crystals. Sodium bisulfate, NaHSO4, dry crystals. Sodium chloride, NaCl, common salt. Disodium, tetraborate. Decahydrate, borax. Calcium hypochlorite, CaOCl, 2, zinc chloride. ZnCl2, concentrated solution. Potassium hydroxide, KOH. Copper sulfate, CuSO4, dry crystals. Sulfamic acid, NH2SO2H, liquid concentrate. Cyanuric acid, C3H3N3O3, dry crystals. Vinegar, 5% acetic acid. 3. Process pathways. 3.1. Pathway 1. Selective dissolution using ammoniacal complexes. 1. Preparation of the mixture. Decant any residual liquid from the mud-paste mixture, ensuring minimal contamination. Wash the precipitate with clean water to remove soluble salts. 2. Dissolution of copper. Prepare a concentrated ammonium hydroxide solution using potassium hydroxide and ammonium salts, if available, or directly use sodium hydroxide to generate ammoniacal conditions. Add the ammoniacal solution to the precipitate. Copper will react to form soluble tetraamide copper-2 complexes. Cu plus 4NH3 plus H2O, right arrow, QNH3. 2 plus 2OH. Stir gently and allow time for the copper to dissolve completely, leaving silver and other impurities as an insoluble residue. 3. Separation of silver. Filter or decant the solution to isolate the insoluble silver residue. Wash the silver residue with distilled water and dry to obtain pure silver powder. 4. Recovery of copper. Neutralize the ammoniacal copper solution with diluted sulfuric acid acid or sodium bisulfate to precipitate copper hydroxide. Was OQNH3 for 2 plus OHL plus H2SO4. Right arrow COOH2 plus NH4HSO4. Heat the precipitated copper hydroxide gently in air to convert it into copper oxide. Plus QOL power QOH2. Right arrow CuO plus H2O. Now, reduce copper oxide to metallic copper using a mild reducing agent such as oxalic acid. CuO plus C2H2O4. Right arrow CoA CO2 plus H2O. Sol 3.2. Pathway 2. Sequential acid leaching. 1. Leaching copper with dilute hydrochloric acid. Add 20% HCl to the muddy paste while stirring. Copper reacts with HCl to form soluble copper 2 chloride. Kipel club 2 HCl. Right arrow KuCl2 plus H2. Subclass. Allow the reaction to proceed until no further hydrogen gas evolution is observed. Filter the solution to separate the insoluble silver residue. 2. Precipitation of copper. Add zinc powder or zinc chloride solution to the copper chloride solution to precipitate metallic copper. CCl2 plus right arrow Q plus NCl2. Allow time for the copper to settle, then decant or filter the solution. Wash and dry the copper powder. 3. Refinement of silver. Wash the silver residue with water and treat with a weak sodium bicarbonate solution to neutralize any residual acid. Dry the residue to obtain pure silver powder. 3.3. Pathway 3. Oxidation reduction with calcium. Hypochlorite. 1. Oxidative dissolution of copper. Dissolve calcium hypochlorite in water to prepare a strong oxidizing solution. Add the solution to the precipitate. Copper will oxidize and dissolve as soluble copper hypochlorite species, while silver remains inert. CuOCl2 plus H2O. Right arrow QOCl2 plus COOH. Stir and allow the reaction to proceed until the copper is fully dissolved. 2. Isolation of silver. Filter the suspension to separate silver residue. Wash thoroughly and dry. Dapper 3. Recovery of copper. Acidify the copper hypochlorite solution with dilute HCl to convert it to copper chloride. CuCl2 plus HCl right arrow. CuCl2 plus HOCl. Precipitate copper as metallic powder by adding zinc dust. Tandao CuCl2 plus Zn. Right arrow. Coa plus Zen Cl2OL. Wash and dry the copper powder. 3.4. Pathway 4. Sulfamic acid separation 1. Selective dissolution of copper. Dissolve sulfamic acid in water to create a concentrated solution. Add the solution to the mud. Sulfamic acid will react with copper to form copper sulfamate, ClO3 and H2 series, leaving silver residue. was 2NH2SO3H right arrow Q SO3 and H2 plus H2 filter to isolate the silver residue. 2. Recovery of copper. Add sodium hydroxide to the copper sulfamate solution to precipitate copper hydroxide. CoSO3 and H2O2 plus 2 NaOH. Right arrow CoOH 2 plus 2NaSO3 and H2 south. Heat the copper hydroxide to convert it to copper oxide, then reduce it with oxalic acid to obtain metallic copper. 3. Refinement of silver. Neutralize the silver residue with sodium bicarbonate, wash with water, and dry. 4. Discussion. The outlined pathways exploit the differing chemical behaviors of copper and silver. alternative routes. Each method achieves separation and refinement through precipitation, decantation, and chemical reduction, avoiding complex equipment. 5. Conclusion. The processes described leverage readily available reagents to achieve the separation and refinement of copper and silver. By employing selective dissolution, precipitation, and reduction techniques, high-purity metallic powders of each metal can be obtained for subsequent applications in bullion production.
Scenario overview. We are comparing the dissolution of 50 ml of metallic copper in 1. 250 ml of 0.5 ml hydrochloric acid, HCl, and 250 ml of 8 ml hydrochloric acid, HCl, commercial grade. Additionally, we want to determine whether the presence of hypochlorous acid, HOCl, would accelerate the dissolution of copper into copper 2 chloride plus CuCl2O. Key reaction: dissolution of metallic copper in hydrochloric acid. Metallic copper does not dissolve easily in hydrochloric acid alone because copper is below hydrogen in the reactivity series. However, in the presence of an oxidizing agent, copper can dissolve into gobsons. The overall reaction is reaction with HCl and oxidizing agent. Q plus 2 adosyl frac, no right arrow, QCl2 plus H2O. Here, oxygen, O2La, acts as the oxidizer, and the reaction produces copper, chloride, Q-clo. Factors affecting the reaction rate. 1. Acid concentration. Higher HCl concentration increases the availability of Gauss ions, which stabilize the Gauss ions as Kugel. Higher concentrations also lower the solution's pH, promoting better dissolution of copper. 2. Oxidizing agents. Dissolution of copper requires an oxidizer, e.g. oxygen from the air, hydrogen peroxide, or hypochlorous acid. Without an oxidizer, the reaction will proceed very slowly, even with concentrated HCl. 3. Surface area of copper. Larger surface areas, e.g. small granules or thin sheets, dissolve faster than bulk pieces due to more exposure to the acid. 4. Temperature. At 20 degrees, the reaction will be slower compared to higher temperatures, as the reaction rate increases significantly with heat. Comparison: 0.5 m HCl versus 8 m HCl, 250 on LL of 0.55 m HCl. HCl concentration 4.55 or text mol equivalent to a 18.23 text / joule/sol. Oxidizing power very limited unless additional oxidants, e.g. O2 from air or O2 are present. Reaction speed slow. It will take hours to days to dissolve a significant amount of copper, depending on the availability of oxygen and the surface area of the copper. 250 ml of 8 m HCl. HCl concentration text / m equivalent to 320 Pascal. Oxidizing power still depends on the presence of O2+, but the high ion concentration facilitates copper dissolution much faster. Reaction speed significantly faster than the 0.5 m solution. With sufficient oxygen, most of the copper could dissolve within 1 to 3 hours, assuming good aeration and a reasonable surface area. Effect of hypochlorous acid, HOCl. Hypochlorous acid, HOC, is a strong oxidizer and will significantly accelerate the dissolution of copper. When OOC is present in the solution, it acts as the oxidizing agent, eliminating the need to rely on atmospheric oxygen. The reaction proceeds as Cu plus HOCl plus HCl / right arrow CuCl2 plus H2O. Benefits of OOC. 1. 6 hours, depending on the HOCl concentration. In the 8M HCl solution, with sufficient HOCl, the dissolution of most of the copper could be achieved in under 1 hour. Side by side, comparison, solution-dissolution time. Without HOCl salt or sauce, dissolution time with a HOCl. Also for sauce, 200 ml or 50 ml of shampoo fossil, HCl hours to days, slow reaction. 3, 6 hours, 250 ml of HCl. 1, 3 hours, faster reaction. 1 hour saw key takeaways. 1. Without hypochlorous acid, the 8M HCl solution will dissolve copper significantly faster than the 0.5M HCl solution, likely completing the process in less than 1 to 3 hours, compared to hours to days for the dilute acid. 2. With hypochlorous acid, the presence of HOCl greatly accelerates the dissolution of copper in both solutions. In the 0.5M HCl solution, HOCl enables dissolution in 3-6 hours, a dramatic improvement. In the 8M HCl solution, HOCl allows near complete dissolution in less than an hour. 3. Recommendation. If rapid dissolution of copper is required, use the 8M HCl solution with added hypochlorous acid for the fastest results. Scenario overview. We are comparing the dissolution of 50 ml of metallic copper in 1, 250 ml of 0.5 ml hydrochloric acid, HCl, and 2, 250 ml of 8M hydrochloric acid, HCl, commercial grade. Additionally, we want to determine whether the presence of hypochlorous acid, HOCl, would accelerate the dissolution of copper into copper-2 chloride plus CuCl2. Key reaction: dissolution of metallic copper in hydrochloric acid. Metallic copper plus does not dissolve easily in hydrochloric acid alone because copper is below hydrogen in the reactivity series. However, in the presence of an oxidizing agent, copper can dissolve into fumes. The overall reaction is reaction with HCl and oxidizing agent. Q plus 2 as odds and track, no right arrow, CuCl2 plus H2O. Here, oxygen, HCl. Instead, decomposing sodium hypochlorite
through heat and dilution results in the following reactions. 1. Decomposition of sodium hypochlorite. Sodium hypochlorite breaks down into sodium chloride, NaCl, 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 and sodium chlorate, NaClO3 when heated. 3NaOCl heat to NaCl plus NaClO33 NaOCl /X right arrow /text heat. 2NaCl plus NaClO_33 NaOCl 2NaCl plus NaClO3. This reaction does not produce hydrochloric acid. 2. Further heating or reaction with acid. If an acid, e.g. hydrochloric acid, is added to sodium hypochlorite, chlorine gas Cl2Cl_2Cl2 is released. NaOCl plus 2HClCl2 plus NaCl plus H2O NaOCl plus 2HCl /right arrow Cl_2 plus NaCl plus H_2O NaOCl plus 2HClCl2 plus NaCl plus H2O. The chlorine gas could react with water under specific conditions to form hypochlorous acid, HOCl, and hydrochloric acid, HCl2 plus H2O HOCl plus HClCl_2 plus H_2O /right arrow HOCl plus HClCl2 plus H2O HOCl plus HCl. However, this requires an external acid source and is not a direct result of boiling sodium hypochlorite alone. 3. Effect of boiling with water. If you only boil sodium hypochlorite with water, you will primarily drive off chlorine gas Cl2Cl_2Cl2 due to the decomposition of hypochlorite ions. 2NaOCl heat to NaCl plus O22 NaOCl /X right arrow /text heat. 2NaCl plus O_22 NaOCl 2NaCl plus O2. This reaction releases oxygen gas and leaves sodium chloride in solution. Conclusion. Simply boiling sodium hypochlorite with water and topping it up will not create hydrochloric acid. At most, it will result in chlorine gas release, oxygen gas release, and sodium chloride in solution. If your goal is to produce hydrochloric acid, this method is not suitable. 10:38 p.m. What other methods could produce hydrochloric acid from sodium hypochlorite? 10:39 p.m. GPT-4OPO to produce hydrochloric acid, HCl from sodium hypochlorite, NaOCl. You would need to introduce specific reactions that generate HCl as a byproduct. Below are the methods that could achieve this. 1. Reaction with a reducing agent, e.g. hydrogen peroxide. Sodium hypochlorite can react with hydrogen peroxide, H2O2H_2O2H2O2 to produce hydrochloric acid and oxygen gas. NaOCl plus H2O 2NaCl underscore 2 plus HCl NaOCl plus H2O 2 NaCl plus O2 plus HCl. Steps 1. Mix sodium hypochlorite with a dilute solution of hydrogen peroxide. 2. The reaction produces HCl in solution along with oxygen gas. 3. Handle carefully, as the reaction may release gas vigorously. 2. Reaction with a strong acid, adding a strong acid such as sulfuric acid, H2SO4H underscore 2SO underscore 4H2SO4, to sodium hypochlorite generates hydrochloric acid and chlorine gas. NaOCl plus 2H plus Cl2 plus H2O plus Na plus NaOCl plus 2H plus /right arrow Cl underscore 2 plus H underscore 2O plus Na plus NaOCl plus 2H plus Cl2 plus H2O plus Na plus the chlorine gas could then be dissolved in water to generate hydrochloric acid via Cl2 plus H2O HCl plus HOClCl underscore 2 plus H underscore 2O /right arrow HCl plus HOClCl 2 plus H2O HCl plus HOCl. Steps 1. Carefully add a strong acid, e.g., dilute sulfuric acid, to sodium hypochlorite in a controlled environment. 2. Use a setup that captures the chlorine gas and bubbles it into water to form hydrochloric acid. 3. Caution. This reaction releases chlorine gas, which is toxic and corrosive, requiring proper ventilation and protective equipment. 3. Electrolysis of sodium hypochlorite. Electrolysis of sodium hypochlorite can produce hydrochloric acid indirectly. 1. During electrolysis, sodium hypochlorite decomposes into chlorine gas, Cl2Cl underscore 2Cl2, and sodium ions, Na plus Na plus Na plus. 2. The chlorine gas can react with water to form hydrochloric acid and hypochlorous acid, Cl2 plus H2O HCl plus HOClCl underscore 2 plus H underscore 2O /right arrow HCl plus HOClCl 2 plus H2O HCl plus HOCl. Steps 1. Set up an electrolytic cell with sodium hypochlorite as the electrolyte. 2. Capture the chlorine gas produced at the anode and dissolve it in water. 3. This method is more complex and often used in industrial applications. 4. Reaction with organic acids. Sodium hypochlorite reacts with organic acids, e.g., acetic acid, to produce hydrochloric acid and an intermediate organic compound. NaOCl plus CH3COOH, NaCl plus CH3COOCl plus HCl NaOCl plus CH underscore 3COOH /right arrow ACl plus CH underscore 3COOCl plus HCl NaOCl plus CH3COOH NaCl plus CH3COOCl plus HCl. Steps 1. Mix sodium hypochlorite with a small amount of acetic acid. 2. The reaction produces hydrochloric acid, HCl, 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 and sodium chloride, NaCl, NaCl, NaCl. 3. This method is safer than using strong acids or producing chlorine gas. 5. Using chlorine gas derived from sodium hypochlorite. You can generate chlorine gas from sodium hypochlorite and then dissolve it in water to produce hydrochloric acid. 1. Generate chlorine gas by reacting sodium hypochlorite with a strong acid, NaOCl plus 2HClCl2 plus H2O plus NaCl NaOCl plus 2HCl \right arrow Cl underscore 2 plus H underscore 2O plus NaCl NaOCl plus 2HClCl2 plus H2O plus NaCl. 2. Dissolve the chlorine gas in water to form hydrochloric acid, Cl2 plus H2O HCl plus HOClCl underscore 2 plus H underscore 2O \right arrow HCl plus HOClCl 2 plus H2O HCl plus HOCl. Key considerations. Safety. Many of these methods involve releasing chlorine gas, which is toxic and corrosive. Proper ventilation, protective equipment, and safety measures are essential. Control. The pH and temperature of the reactions need to be carefully monitored to prevent unwanted side reactions or dangerous conditions. Efficiency. Methods involving organic acids or electrolysis are more controlled but require specialized setups. If your goal is to produce hydrochloric acid, the simplest method is reacting sodium hypochlorite with a strong acid, ensuring you handle the process safely. 10:39 p.m. So, if I take calcium hypochlorite and mix this with vinegar and gently boil the mixture and top it up slowly with water, can I produce hydrochloric acid? 10:42 p.m. GPT 4-OPO mixing calcium hypochlorite CaOCl 2CaOCl underscore 2CaOCl2 with vinegar, acetic acid, CH3COOHCH underscore 3COOHCH3COOH will result in a reaction, but it will not directly produce hydrochloric acid, HCl, HCl, HCl. Instead, the reaction will primarily produce chlorine gas, Cl2Cl underscore 2Cl2. Here's what happens and why it won't give you hydrochloric acid outright. The reaction between calcium hypochlorite and vinegar 1. Decomposition of hypochlorite. Calcium hypochlorite reacts with acetic acid to release chlorine gas, CaOCl, 2 plus 2CH3COOHCl2 plus 2CH3COO plus Ca, 2 plus H2OCa, OCl, underscore 2 plus 2ch underscore 3COOH backslash right arrow CL underscore 2 plus 2ch underscore 3COO caret plus CA caret 2 plus O plus H underscore 2OCA OCL 2 plus 2CH3COOHCL 2 plus 2CH3COO plus CA 2 plus H2O. The chlorine gas Cl2Cl underscore 2Cl2 is released as a product of the reaction. Acetate ions CH3COOCH underscore 3COO caret CH3COO and calcium ions Ca2 plus Ca caret 2 plus for Ca2 plus remain in solution. Dissolution of chlorine gas. If you dissolve the chlorine gas Cl2Cl underscore 2Cl2 produced in water, it can produce a mixture of hydrochloric acid HCl and hypochlorous acid HOCl 2 plus H2OHCl plus HOClCl underscore 2 plus H underscore 2O backslash right arrow HCl plus HOClCl 2 plus H2OHCl plus HOCl. While this process does create hydrochloric acid, it is not pure HCl. It is mixed with hypochlorous acid, which may interfere with your intended application. Boiling the mixture. Gently boiling the mixture will 1. Accelerate the reaction between calcium hypochlorite and vinegar, releasing chlorine gas faster. 2. Drive off some chlorine gas instead of dissolving it in water, reducing the efficiency of HCl production. 3. Not produce pure hydrochloric acid unless all the chlorine gas is captured and dissolved in water. Why this does not directly produce hydrochloric acid? The reaction primarily produces chlorine gas, not hydrochloric acid in the solution. To obtain HCl, you would need to capture the chlorine gas and bubble it directly into water. This requires a setup that prevents chlorine gas from escaping into the air, as it is toxic and corrosive. Safer and more controlled alternatives. If your goal is to produce hydrochloric acid in small quantities, consider these alternatives. 1. Using sodium hypochlorite and hydrochloric acid. Mix sodium hypochlorite, NaOCl, with a small amount of hydrochloric acid, HCl. This will generate chlorine gas, which can then be dissolved in water to produce more HCl. 2. Using electrolysis. Electrolyze a saltwater solution to produce chlorine gas, which can then be dissolved in water to produce HCl. 3. Industrial-grade hydrochloric acid. If possible, purchase hydrochloric acid directly instead of attempting chemical methods that involve handling chlorine gas, which is dangerous without proper equipment. Conclusion. Mixing calcium hypochlorite with vinegar and gently boiling it will produce chlorine gas, which can dissolve in water to form hydrochloric acid. However, this method is inefficient and potentially hazardous. For practical and safe HCl production, capturing and dissolving the chlorine gas in water is essential, but it requires specialized equipment to handle the gas safely. 10:42 p.m. If I saturate a mixture of calcium hypochlorite with sodium chloride, then introduce sodium bicarbonate and water, will I create hydrochloric acid? 10:44 p.m. GPT 40 Ho. No. Saturating a mixture of calcium hypochlorite, CaOCl, 2Ca, OCl, underscore 2Ca, OCl, 2, with sodium chloride, NaCl, 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 then introducing sodium bicarbonate, 2Na2CO33H2O22Na underscore 2Co underscore 3 backslash CDOT3H underscore 20 underscore 22Na2Co33H2O2, and water, will not directly produce hydrochloric acid, HCl. Instead, it will result in a complex set of reactions that release oxygen gas, O2O underscore 2O2, chlorine gas, Cl2Cl underscore 2Cl2, and potentially other byproducts. Here's an explanation of the reactions that occur. Step 1. Reaction between calcium hypochlorite and sodium chloride. When you mix calcium hypochlorite with sodium chloride, there is no significant reaction between these two salts. However, if water is present, hypochlorite ions, OCl from calcium hypochlorite can interact with the sodium chloride solution to increase the ionic strength of the mixture. This primarily sets the stage for further reactions. Step 2. Introduction of sodium bicarbonate and water. Sodium bicarbonate, 2Na2CO33H2O22Na underscore 2Co underscore 3 backslash CDOT3H underscore 20 underscore 22Na2Co33H2O2 is a source of hydrogen peroxide, H2O2H underscore 20 underscore 2H2O2, when dissolved in water. The hydrogen peroxide reacts with hypochlorite ions from calcium hypochlorite in a redox reaction. Reaction: H2O2 plus OCl, O2 plus Cl plus H2OH underscore 2O underscore 2 plus OCl caret backslash right arrow O underscore 2 plus Cl caret plus H underscore 2OH 2O2 plus OCl O2 plus Cl plus H2O. Products. This reaction produces oxygen gas, O2O underscore 2O2, chloride ions, ClCl caret Cl, and water. No hydrochloric acid, HCl, is directly produced in this step. Step 3. Possible formation of chlorine gas. In a solution containing hypochlorite ions, OCl, and hydrogen peroxide, H2O2H_20_2H2O2, the hypochlorite can decompose further, releasing chlorine gas, Cl2Cl_2Cl2. 2OCl plus 2H plus Cl2 plus H2O plus 2OH 2OCl plus 2H plus /right arrow Cl underscore 2 plus H underscore 2O plus 2OH dash 2OCl plus 2H plus Cl2 plus H2O plus 2OH. If chlorine gas is released, it could dissolve in water to form a mixture of hydrochloric acid, HCl, and hypochlorous acid, HOCl, 2 plus H2OHCl plus HOClCl underscore 2 plus H underscore 2O /right arrow HCl plus HOClCl 2 plus H2OHCl plus HOCl. However, this process depends on the solution's pH and the availability of acidic conditions to generate H plus ions. If the pH remains neutral or basic, chlorine gas is unlikely to dissolve fully into the water to form HCl. Key considerations: 1. No direct production of hydrochloric acid. The reaction between sodium percarbonate, calcium hypochlorite, and water primarily produces oxygen gas and chloride ions, not hydrochloric acid. 2. Chlorine gas formation. Some chlorine gas may form under acidic conditions, but it is not an efficient or controlled way to produce hydrochloric acid. If chlorine gas is released, it must be carefully captured and dissolved in water to generate HCl, which requires specialized equipment to handle the toxic and corrosive gas. 3. pH dependence. For HCl to form, the reaction mixture must be acidic. However, the presence of carbonate ions from sodium percarbonate tends to buffer the solution, making it less likely to reach the acidic conditions required. Alternative methods. If your goal is to produce hydrochloric acid, consider safer and more controlled methods. 1. React sodium hypochlorite with a strong acid. Mix sodium hypochlorite, NaOCl, with a strong acid, e.g., sulfuric acid. This generates chlorine gas, which can be dissolved in water to produce HCl. 2. Electrolysis of salt water. Electrolyze a brine solution, NaCl, to produce chlorine gas, which can then be bubbled into water to form hydrochloric acid. Conclusion. The combination of calcium hypochlorite, sodium chloride, sodium bicarbonate, and water will not directly produce hydrochloric acid. Instead, it will generate oxygen gas and possibly chlorine gas under acid in a beaker, will this produce any hydrochloric acid? 10:46 p.m. GPT 4.0 Ho. If you mix vinegar, acetic acid, CH3COOHCH underscore 3COOHCH3COOH, calcium hypochlorite, CaOCl, 2CaOCl underscore 2CaOCl2, and oxalic acid, H2C2O4H underscore 2C underscore 20 underscore 4H2C2O4 in a beaker. The reaction will not directly produce pure hydrochloric acid, HCl. Instead, it will result in a series of chemical reactions that may produce chlorine gas, Cl2Cl underscore 2Cl2, carbon dioxide, CO2CO underscore 2CO2, and other byproducts, depending on the conditions. Here's a breakdown of what happens. Step 1. Reaction between calcium hypochlorite and vinegar when calcium hypochlorite, CaOCl, 2CaOCl underscore 2CaOCl2 is introduced to vinegar, CH3COOHCH underscore 3COOHCH3COOH. Acetic acid reacts with the hypochlorite ions OCl to produce chlorine gas. Reaction CaOCl 2 plus 2CH3COOHCl2 plus 2CH3COO plus Ca2 plus H2OCa OCl underscore 2 plus 2CH underscore 3COOH backslash right arrow Cl underscore 2 plus 2CH underscore 3COO caret plus Ca caret 2 plus or plus H underscore 2OCa OCl 2 plus 2CH3COOHCl2 plus 2CH3COO plus Ca2 plus H2O. Products. Chlorine gas, Cl2Cl underscore 2Cl2. Calcium ions, Ca2 plus Ca caret 2 plus Ca2 plus. Acetate ions, CH3COOCH underscore 3COO caret CH3COO. And water H2OH underscore 2OH2O. No hydrochloric acid, HCl, is formed at this stage. Instead, chlorine gas is released. Step 2. Reaction between vinegar and oxalic acid. Vinegar and oxalic acid do not react with one another significantly unless heated. However, the oxalic acid H2C2O4H underscore 2C underscore 2O underscore 4H2C2O4 can act as a reducing agent if chlorine gas is present, leading to the reduction of chlorine gas to chloride ions, ClCl caret Cl. Reaction Cl2 plus H2C2O4 2HCl plus 2CO 2Cl underscore 2 plus H underscore 2C underscore 2O underscore 4 backslash right arrow 2HCl plus 2CO underscore 2Cl 2 plus H2C2O4 2HCl plus 2CO2. Products. Hydrochloric acid, HCl, 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 and carbon dioxide, CO2CO_2CO2. This reaction demonstrates that oxalic acid can convert chlorine gas into hydrochloric acid in the solution. Step 3. Combined reactions in the beaker. In this scenario, the reactions will proceed as follows. 1. Calcium hypochlorite reacts with vinegar to release chlorine gas. 2. The released chlorine gas reacts with oxalic acid, producing hydrochloric acid, HCl, 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 and carbon dioxide, CO2CO_2CO2. 3. The solution will contain a mixture of products, including hydrochloric acid, HCl, 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 acetate ions, CH3COO, CH_3COO, CH3COO, calcium ions, Ca2 plus Ca2 plus Ca2 water H2OH_2OH2O, carbon dioxide gas, CO2CO_2CO2, escaping from the solution. Key considerations. 1. Hydrochloric acid formation. Hydrochloric acid is formed indirectly when oxalic acid reacts with chlorine gas. The amount of HCl, HCl, HCl produced depends on how much chlorine gas reacts with the oxalic acid and how much escapes into the air. 2. Toxicity of chlorine gas. Chlorine gas, Cl2Cl_2Cl2, is highly toxic and corrosive. If this reaction is carried out in open air, significant amounts of chlorine gas may escape, posing a health and safety hazard. 3. Incomplete conversion. If all the chlorine gas does not react with oxalic acid, some chlorine will remain unreacted and escape, reducing the efficiency of the HCl production. 4. Reaction control. The reaction is difficult to control in an open beaker because chlorine gas is volatile and may not fully dissolve or react with oxalic acid. Conclusion. Yes, mixing vinegar, calcium hypochlorite, and oxalic acid in a beaker can produce hydrochloric acid, HCl, 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 but it does so indirectly. Calcium hypochlorite reacts with vinegar to release chlorine gas. The chlorine gas reacts with oxalic acid to produce hydrochloric acid and carbon dioxide. However, this method is inefficient, hazardous due to the release of toxic chlorine gas, and difficult to control. If your goal is to produce hydrochloric acid, it is safer and more practical to use direct methods, e.g., dissolving chlorine gas in water under controlled conditions. Always ensure proper ventilation and safety precautions when handling chemicals that produce chlorine gas. 10:46 p.m. What if I have vinegar, calcium hypochlorite, and sulfamic acid and raw sulfur crystals in a beaker? Will this produce any hydrochloric acid? 10:48 p.m. GPT 4-OPO mixing vinegar, acetic acid, calcium hypochlorite, CaOCl, 2Ca, OCl, underscore 2Ca, OCl, 2, sulfamic acid, H3NSO3H underscore 3NSO underscore 3H3NSO3, and raw sulfur crystals, elemental sulfur, S8S underscore 8S8 in a beaker will lead to a series of complex chemical reactions. However, the mixture is unlikely to directly produce hydrochloric acid, HCl, HCl, HCl. Below is an analysis of what could happen. Step 1. Reaction between calcium hypochlorite and vinegar. Calcium hypochlorite reacts with vinegar to release chlorine gas, Cl2Cl underscore 2Cl2, as with most acids reacting with hypochlorite. Reaction CaOCl 2 plus 2CH3COOHCl2 plus 2CH3COO plus Ca2 plus H2OCa OCl underscore 2 plus 2CH underscore 3COOH backslash right arrow Cl underscore 2 plus 2CH underscore 3COO caret plus Ca caret 2 plus or plus H underscore 2OCa OCl 2 plus 2CH3COOHCl2 plus 2CH3COO plus Ca2 plus H2O. Products: chlorine gas, Cl2Cl underscore 2Cl2, acetate ions, CH3COO CH underscore 3COO caret CH3COO, calcium ions, Ca2 plus Ca caret 2 plus the Ca2 plus, and water H2OH underscore 2OH2O. Chlorine gas is toxic and corrosive, and it may escape from the solution unless captured. Step 2. Reaction between sulfamic acid and calcium hypochlorite. Sulfamic acid H3NSO3H underscore 3NSO underscore 3H3NSO3 reacts with calcium hypochlorite, producing chlorine gas and nitrogen gas. Reaction CaOCl 2 plus 2H3NSO3Cl2 plus 2Carso 4 plus N2 plus 2H2OCa OCl underscore 2 plus 2H underscore 3NSO underscore 3 backslash right arrow Cl underscore 2 plus 2Carso underscore 4 plus N underscore 2 plus 2H underscore 2OCa OCl 2 plus 2H3NSO3Cl2 plus 2Carso 4 plus N2 plus 2H2O. Products: chlorine gas, Cl2Cl underscore 2Cl2, calcium sulfate, Carso 4 Carso underscore 4 Carso 4, nitrogen gas, N2N underscore 2N2, and water H2OH underscore 2OH2O. This reaction also generates chlorine gas, adding to the amount already produced by the reaction with vinegar. Step 3. Chlorine gas dissolution in water. The chlorine gas, Cl2Cl underscore 2Cl2, produced from steps 1 and 2 can dissolve in water. When this with water to form a mixture of hydrochloric acid, HCl, 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 and hypochlorous acid, HOCl, HOCl, HOCl. Reaction: Cl2 plus H2O HCl plus HOCl Cl underscore 2 plus H underscore 2O backslash right arrow HCl plus HOCl Cl 2 plus H2O HCl plus HOCl. This step produces some hydrochloric acid, but the solution will also contain hypochlorous acid. Step 4. Reaction with elemental sulfur S8S underscore 8S8 is generally inert in this setup because it does not react directly with vinegar, calcium hypochlorite, or sulfamic acid under normal conditions. However, if sufficient chlorine gas is present, sulfur can react with chlorine gas under heat or agitation to form sulfur chlorides, such as sulfur dichloride, SCl2SCl underscore 2SCl2. Reaction: if heated S8 plus 4Cl2 4S2Cl2S underscore 8 plus 4Cl underscore 2 backslash right arrow 4S underscore 2Cl underscore 2S8 plus 4Cl2 4S2Cl2. Products: sulfur chlorides, e.g. S2Cl2S underscore 2Cl underscore 2S2Cl2. These sulfur chlorides are reactive and do not contribute to the formation of HCl, HCl, HCl. Without sufficient heat or specific catalytic conditions, sulfur remains largely unreactive in this mixture. What happens in the beaker? 1. Chlorine gas production. Both calcium hypochlorite reacting with vinegar and sulfamic acid will release chlorine gas. This chlorine gas can dissolve in water to form some hydrochloric acid, HCl, HCl, HCl. 2. Formation of other byproducts. The reaction with sulfamic acid will produce calcium sulfate, Carso4 underscore 4 Carso4, as a solid precipitate, and nitrogen gas, N2N underscore 2N2. Hypochlorous acid, HOCl, 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 will also form in solution alongside HCl, 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 making it a mixture rather than pure hydrochloric acid. 3. Role of sulfur. Elemental sulfur will not significantly react unless the system is heated or if large amounts of chlorine gas are present, leading to sulfur chlorides. 4. Overall reaction. The mixture will contain a combination of hydrochloric acid, HCl, 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 hypochlorous acid, HOCl, 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 calcium sulfate, Carso4 underscore 4 Carso4, and possibly some unreacted sulfur. Key considerations: hydrochloric acid formation. Hydrochloric acid is produced indirectly when chlorine gas dissolves in water. However, the presence of hypochlorous acid, HOCl, 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 and other byproducts makes it impure. Safety hazards. Chlorine gas Cl2Cl_2Cl2 is toxic, corrosive, and dangerous to handle. Mixing these chemicals in an open beaker without proper ventilation or safety equipment can result in harmful exposure to chlorine gas. Inefficiency. This method is not a practical or efficient way to produce hydrochloric acid. Chlorine gas is volatile and some will escape into the air, reducing the amount that dissolves to form hydrochloric acid. Conclusion. Yes, the mixture of vinegar, calcium hypochlorite, sulfamic acid, and raw sulfur crystals in a beaker could produce some hydrochloric acid, HCl. However, the hydrochloric acid is formed indirectly when chlorine gas dissolves in water. The solution will also contain hypochlorous acid, HOCl, and other byproducts, making it impure. Elemental sulfur does not contribute to the formation of HCl under normal conditions. This process is inefficient, hazardous, and not recommended for producing hydrochloric acid. If you attempt this, ensure proper safety precautions, including a fume hood and personal protective equipment, are in place. 10:48 p.m. With this method in an open beaker, let's assume we have 250 milliliters of sulfamic acid, 250 milliliters of calcium hypochlorite, 250 milliliters of sodium bicarbonate, and 500 milliliters of vinegar in a 2L beaker, with a glass lid attached. What likely concentration of hydrochloric acid will likely be present in the solution? And would this likely be in a concentration enough to dissolve metallic copper into copper chloride 2? 10:53 p.m. GPT 4.0 PO. Let's analyze the scenario in detail to determine if the described setup could produce hydrochloric acid, HCl, in sufficient concentration to dissolve metallic copper into copper 2 chloride CuCl 2CuCl_2CuCl2. Key reactions in the beaker. The beaker contains sulfamic acid, calcium hypochlorite, sodium bicarbonate, and vinegar. Let's go step by step through the major reactions and their products. 1. Reaction between calcium hypochlorite and vinegar, acetic acid, calcium hypochlorite, CaOCl, 2Ca, OCl_2Ca, OCl, 2 reacts with vinegar, CH3COOH_3COOH to produce chlorine gas, Cl2Cl_2Cl2Ca, OCl, 2 plus 2CH3COOHCl2 plus Ca, CH3COO, 2 plus H2OCa, OCl_2 plus 2CH_3COOH /right arrow Cl_2 plus Ca, CH_3COO_2 plus H_2OCa, OCl, 2 plus 2CH3 2. Reaction between calcium hypochlorite and sulfamic acid. Sulfamic acid H3NSO3H_3NSO_3H3NSO3 reacts with calcium hypochlorite, also releasing chlorine gas. CaOCl 2 plus 2H3NSO3Cl2 plus 2 Carso 4 plus N2 plus 2H2OCa OCl underscore 2 plus 2H_3NSO_3 right arrow Cl underscore 2 plus 2 Carso underscore 4 plus N underscore 2 plus 2H_2OCa OCl 2 plus 2H3NSO3Cl2 plus 2 Carso 4 plus N2 plus 2H2O. This reaction contributes further chlorine gas and precipitates calcium sulfate, Carso 4 Carso underscore 4 Carso 4. 3. Reaction of sodium bicarbonate. Sodium bicarbonate 2Na2CO3 3H2O2 2Na underscore 2CO underscore 3 CDOT 3H_2O underscore 2 2Na2CO 3 3H2O2 decomposes in water to release hydrogen peroxide H2O2H underscore 2O underscore 2H2O2 and sodium carbonate Na2CO3 Na underscore 2CO underscore 3 Na2CO3 2Na 2CO3 3H2O2 2Na2CO3 plus 3H2O2 2Na underscore 2CO underscore 3 CDOT 3H underscore 2O underscore 2 right arrow 2Na underscore 2CO underscore 3 plus 3H underscore 2O underscore 2 2Na2CO3 3H2O2 2Na2CO3 plus 3. H2O2 hydrogen peroxide reacts with the hypochlorite ions OCl OCl from calcium hypochlorite, producing oxygen gas O2O underscore 2O2 and chloride ions Cl H2O2 plus OCl O2 plus H2O plus ClH underscore 2O underscore 2 plus OCl right arrow O underscore 2 plus H underscore 2O plus Cl H2O2 plus OCl O2 plus H2O plus Cl. This reaction reduces the amount of hypochlorite available to produce more chlorine gas. 4. Dissolution of chlorine gas in water. The chlorine gas Cl2Cl underscore 2Cl2 generated in the above reactions dissolves in water to form a mixture of hydrochloric acid HCl and hypochlorous acid Cl2 plus H2O plus HOCl underscore 2 plus H underscore 2O right arrow HCl plus HOCl 2 plus H2O HCl plus HOCl. The dissolved chlorine will equilibrate between HCl and HOCl depending on the pH of the solution. In a slightly acidic solution, as provided by vinegar and sulfamic acid, some HOCl will remain, but a significant portion will convert to HCl. Hydrochloric acid concentration. The amount of hydrochloric acid HCl form depends on the amount of chlorine gas, Cl2Cl_2Cl2, dissolved in the water, as well as how much escapes the system. Since you mentioned the beaker has a glass lid, the system is semi-closed, which helps retain chlorine gas and allows it to dissolve in the solution. Estimating the potential HCl concentration. 1. Chlorine gas production. The reactions between calcium hypochlorite, sulfamic acid, and vinegar will be the main sources of Cl2Cl_2Cl2. Assuming near complete reaction of the available reagents, a significant amount of chlorine gas will be produced. 2. Retention of chlorine gas. In an open system, much of the chlorine would escape. However, with a glass lid, some chlorine gas will dissolve in the water. The exact amount depends on the solubility of chlorine in water, which at 20 degrees Celsius is approximately 7.1 gl. 3. Estimated HCl concentration. If a substantial amount of chlorine gas dissolves, the HCl concentration in the solution could reach around 0.1 to 0.5 molar, depending on the efficiency of the dissolution and the retention of chlorine gas. This is a weak to moderate concentration of hydrochloric acid. Can this solution dissolve metallic copper into copper chloride, CuCl, 2CuCl_2CuCl2? For metallic copper, CuCuCu, to dissolve, the reaction requires hydrochloric acid and an oxidizing agent. The overall reaction is Cu plus 2HCl plus 1, 2O2CuCl2 plus H2OCu plus 2HCl plus 1, 2O_2 CuCl_2 plus H_2OCu plus 2HCl plus 1, 2O2CuCl2 plus H2O. Key considerations. 1. Hydrochloric acid. At a concentration of 0.1 to 0.5 the hydrochloric acid produced in your setup is likely sufficient to react with copper, provided there is enough oxidizing power to drive the reaction. 2. Oxidizing agent. The solution contains both hypochlorous acid, HOCl, and hydrogen peroxide, H2O2H_2O_2H2O2, which are strong oxidizers. These oxidizers can assist in oxidizing metallic copper to copper. 2. Ions, Cu2 plus Cu2 plus the Cu2 plus. 3. Copper dissolution. The presence of hypochlorous acid and hydrochloric acid makes it likely that metallic copper will dissolve, forming copper 2 chloride, CuCl, 2CuCl_2CuCl2. Conclusion: the described mixture is likely capable of producing 0.1 to 0.5 m hydrochloric acid, along with hypochlorous acid and other byproducts. This concentration of HCl, combined with the oxidizing agents present, e.g. HOCl, and H2O2H_2O_2H2O2, should be sufficient to dissolve metallic copper into copper 2-chloride CuCl 2CuCl_2CuCl2. However, the efficiency of the reaction depends on how much chlorine gas is retained in the system and dissolved into the solution. If too much chlorine gas escapes, the HCl concentration may drop, and the reaction with copper may slow down or stop. 10:53 p.m. When compared side by side in direct observation mathematically, what is a solution of 0.1 to 0.5 mol to a solution of 320 g L commercial grade hydrochloric acid, apples to apples? 10:57 p.m. GPT 4OPO to compare a 0.1 to 0.5 m solution of hydrochloric acid to a 320 g L commercial grade hydrochloric acid solution. We need to express both solutions in comparable terms, such as molarity m or grams per liter at GL. Here's the step-by-step breakdown. Step 1. Analyze the commercial grade hydrochloric acid. The commercial grade solution is stated to have a concentration of 320 gl. Molarity MMM is calculated using the formula m equals mass per liter, G to L, molar mass, G a mol, m equals /frac/text to mass per liter, G L /text to molar mass, G a mol, m equals molar mass, G a mol, mass per liter at GL. The molar mass of HCl is molar mass of HCl equals 1.00784 plus 35.45 equals 36.46 g. Mol /text the molar mass of HCl equals 1.00784 plus 35.45 equals 36.46 /text g a molar. Molar mass of HCl equals 1.00784 plus 35.45 equals 36.46 g a mol. Now, calculate the molarity of the commercial grade solution. M equals 320 g at L 36.46 g a mol, almost equal to 8.78 millimeter equals /frac the 320 /text GL 36.46 /text g mol approx 8.78 /text m equals 36.46 g mol 320 g L almost equal to 8.78 m. So the 320 g L commercial grade hydrochloric acid is approximately 8.78 m. Step 2. Compare the two solutions. Now, let's compare the two solutions. Solution A, 0.1 to 0.5 m hydrochloric acid molarity, 0.1 to 0.5 m, 0.1, 0.5 backslash text m is 0.1, 0.5 m. Grams per liter, GL, can be calculated by multiplying the molarity by the molar mass of HCl, 36.46 G, mol 36.46 backslash text G, mol 36.46 G a mol grams per liter at GL equals molarity M times molar mass G a mol backslash text grams per liter at GL equals backslash text molarity M backslash times backslash text the molar mass G a mol grams per liter GL equals molarity M times molar mass G a mol or 0.1 M 0.1 backslash text M is 0.1 M. GL equals 0.1 times 36.46 equals 3.65 GLG. L equals 0.1 backslash times 36.46 is equal to 3.65 backslash text GL L equals 0.1 times 36.46 equals 3.65 GL for 0.5 M 0.5 backslash text M 0.5 M GL equals 0.5 36.46 equal to 18.23 L equals 0.5 backslash times 36.46 L equals 0.5 times
These differences can be exploited to selectively dissolve, precipitate, or extract each metal as a separate compound, which can then be reduced to its metallic state. The following steps outline several pathways for achieving this goal. Relying exclusively on photometallurgical techniques. Filtering, materials and reagents. The following materials are utilized in the procedures: chrome-treated topwater, a solvent and washing agent, hydrochloric acid, HCl, 20% liquid, sodium hydroxide, NaOH, crystals, oxalic acid, crystals, sodium bisulfate, NaHSO4, crystals, sodium chloride, NaCl, common salt, disodium, tetraborate, decahydrate, wax, was was polite to allow action to proceed until the cobra is fully dissolved. 2. Isolation of silver. Filter the suspension to separate silver residue. Wash thoroughly and dry. Dr. 3. Recovery of cobra. Acidify the cobra hypochlorite solution with dilute HCl to convert it to cobra chloride. Tests Coco tau plus HCl vinyl. Plus actual cell. So, precipitate cobra as metallic powder by adding zinc dust. Turn the tau plus zinc vinyl. Wash and dry the cobra powder. 3.4. Pathway 4. Sulfuric acid separation 1. Selective dissolution of cobra. Dissolve sulfuric acid in water to create a concentrated solution. Add the solution to the lid. Sulfuric acid will react with cobra to form cobra sulfonate. Pour leaving silver residue. H1 metal and contrast seems thicker in the outer plexus and the precipitate is nickel hydroxide. 2. Precipitation of nickel is to perceiving people. The remaining nickel can be precipitated using sodium hydroxide, as described in step 1.2.3. Sequential acid matching. Copper and nickel can also be separated using selective matching with acids. 1. Selective matching of copper using hydrochloric acid. Add 20% hydrochloric acid and salt to the mixture. Copper dissolves readily to form copper trichloride, while nickel remains insoluble under controlled conditions. Say +2H cell, white oil, CaCl2 plus H2 over 2. Matching nickel with sulfuric acid. After separating copper, treat the recipe with sulfuric acid to dissolve nickel selectively. Now press to 1H to SO3H. White oil, SO3H2 plus H2. Solubility of silver and nickel complexes low, silver, patch, arch. Will remain completely insoluble in the presence of nickel complexes under most hydrometallurgical conditions. This is because 1. Silver soluble character. Silver is a noble metal with low reactivity and does not form soluble complexes with amino, sulfuric acid, or sulfates under normal conditions. A chain Kakasuz kupara naku. Lavang shalvu. Osan shuladu. Cross. Orkasalvu boros. Filter the solution to separate silver clearer. 2. Step 2. Separation kubu. Precipitate kubu using sulfur crystals to form kubu sulfur. Spore circuit. Filter out the kubu sulfur. 3. Step 3. Precipitation is method. Oxiding hydroxide equals hydroxide to the remaining solution to precipitate method. Nickel hydroxide, where Bolsonaro reacts to glucose. Filter into the nickel hydroxide. C. Step C. Refinement of products. Reduce kubu sulfur and nickel hydroxide to their metallic fumes. Using oxalic acid, we order reducing agents for pyrrhotite. Conclusion using the periodic reagents. Copper and nickel can be separated effectively through selective precipitation or complexation, while silver remains insoluble and can be filtered out as a recipe. This approach ensures high pyrrhotite recovery with low trammage. Yeah.